So welcome everyone. I am delighted you were able to join us for today's Mineta Transportation Institute Research Snaps webinar, which is co-sponsored by Econolite. Econolite is an innovator of intelligent transportation system solutions, products, and services committed to employing advanced technologies that reduce travel time, ease congestion, enhance transit operations, provide safer mobility, and improve quality of life. My name is Dr. Hillary Nixon, and I am the Deputy Executive Director of the Mineta Transportation Institute at San Jose State University. MTI leads the Mineta Consortium for Transportation Mobility, funded by the U.S. Department of Transportation, and the California State University Transportation Consortium, funded by the Road Repair and Rehabilitation Act of 2017. Our mission is to increase mobility for all by improving the safety, efficiency, accessibility, and convenience of our nation's transportation system. These days, we hear a great deal about technological advancements and automated vehicles. Automotive companies are constantly striving to enhance their vehicles to minimize and ultimately eliminate driver error and enhance safety. Today's webinar has some exciting and timely information about how these features affect driver behavior and road safety. During the webinar, if you have any questions for our presenters, you can submit them through the chat or Q&A feature in Zoom. We are recording this webinar, and the link to view will be available shortly after the presentation on our website and social media pages. Today's presentation specifically looks at how advanced driver assistance systems, or ADAS, and automated features affect driver behavior and how to keep everyone safe on the road. To learn more about their study methods and findings, let's turn to our researchers. It gives me great pleasure to introduce today's speakers. Here with us today is Raghuveer Gribatla, who is pursuing his PhD in infrastructure and environmental systems at the University of North Carolina at Charlotte, where he also earned his master's degree in transportation engineering. He is fascinated by the intersection of traffic safety and connected and automated vehicles. We also have Dr. Srinivas Pulugurtha with us today. He is a professor and research director in the Department of Civil and Environmental Engineering at the University of North Carolina at Charlotte, where he's director of the Infrastructure, Design, Environment, and Sustainability, or IDEAS, Center there. Srinivas and Raghu, thank you so much for taking the time to be here with us today and share your exciting research. I turn the floor over to you now.
Thank you for the introduction, Dr. Hillary Nixon. I also thank you, MTI and Econolite, for the opportunity to present our work, which is based on a project that we are doing through the consortium led by MTI. As you can see, the focus of our presentation, or the title of our presentation, is Advanced Driver Assistance Systems and Automated Features. Are they really driving us to safety? I'm going to start the presentation and then have Raghu present a few slides, and then I will kind of end the presentation with some quick snaps of the results from our research. If you look at like traffic deaths, it's, as we all know, it's a leading cause of deaths when it comes to people up to 54 years in age. More than 36,000 people are killed, and an additional 2.7 plus million people are injured in 6.7 plus million crashes annually in the United States. If you look at the driver errors, the causes of these crashes, driver errors contribute to 90 to 95% of these crashes, according to the National Safety Council, as well as other researchers. These errors could be categorized into recognition errors, decision errors, performance errors, and non-performance errors. And the economic impact of these crashes exceed, say, $800 million or $900 million per year. While most of these non-performance, most of the errors can be addressed, the non-performance errors are typically hard to kind of fix or solve or mitigate because of the randomness associated with, let's say, these non-performance errors. So when it comes to the other, let's say roughly 80 to 85% of the errors, they could be addressed using advanced features in the vehicles. And that's what we are trying to focus in our project as well as in our presentation today. If you look at like these advanced features, they use sensors with varying detection ranges. Some of these sensors, for example, the smallest range of detection is for parking system that are used at low speeds. Likewise, when it comes to blind spot warning systems, they kind of use like these low range detection sensors that respond to vehicles in adjacent lanes. The longest detection range is typically for those, it's engaged when the vehicles are at higher speeds, typically when you are kind of like on freeways or on high-speed roads, while emergency braking and other collision avoidance systems could use mid to kind of like high range sensors like LiDAR scanners or ultrasound type scanners. The lane detection systems also are kind of based on low detection range sensors. Again, we try to categorize these advanced features into, let's say, warning systems like blind spot warning, lane departure warning, and overspeed warning, for example. An extension, if you look at it from automation perspective, are automated features like lane keep assist and adaptive cruise control or cooperative adaptive cruise control. Now, if we look at like the understanding of vehicle owners, understanding of these features, I mean, there are certainly limitations. I mean, not everybody seems to understand the functionality of these advanced features. Of course, literature documents that, let's say, the automated features are trusted more, but again, they cannot be trusted in all the situations. So while some accept, some do not, there is some confusion, and literature documents some kind of work, but most of the work that's documented in the literature is looking at, let's say, some scenarios that are very amicable for driving, very specific conditions. But the reality is that the behavior certainly could depend on the driver condition, whether you're driving in rural areas or urban areas, whether you're driving in, let's say, whether rainy condition or not. So let's say normal conditions compared to normal conditions. It also depends on the demographic characteristics of the driving history or the socioeconomic characteristics of the drivers. So this kind of like indirectly mandates the need to perform an in-depth analysis of advanced features and compare for various driving conditions. And this is what led to kind of our research objectives, which is to explore and assess the effects of advanced features on driver behavior. So basically look at, let's say, the behavior when drivers are on different classes of roads, whether it's rural highways, freeways, or urban arterials, when they're driving in, let's say, different weather conditions, lighting conditions, and how it varies based on the demographic characteristics and socioeconomic characteristics of the driver. And we used a driver simulator to kind of evaluate, let's say, the effect of these advanced features. And we'll have Raghu discuss the tools that were developed using the driver simulator.
Hi. The whole process of developing a simulation of simulating a scenario in the driver simulator basically takes 3 steps. So the first one is, and this process uses 3 tools in the 3 steps. The first one involves tile mosaic tool. So this is where we basically develop a road network, and this tool offers us different types of tiles of roadways. So you might have different options like for urban roads, rural roads, freeways, intersections, or local roads. So we basically put these different tiles together to form a road network. And this is where the library files from the tile mosaic tool handle the information of what all road tiles have been used for a particular set, or in what we call as a world file that the tile mosaic tool generates. So these library files store the information of what road tiles have been used and in what sequence or what combinations. And then once a world file or a road network which has been generated, it's exported into the next tool, the interactive scenario authoring tool, or the ISAT as we call it. So this is where in this tool, we add different kinds of traffic, weather, and lighting conditions to the simulation. So the traffic conditions include adding vehicles, which vary from heavy semi trucks to pedestrians and bicyclists as well. And along with these, we can also simulate conditions, different weather conditions like rain. And lighting conditions as well. And we can also fabricate scenarios here, like when we are testing certain features, advanced features, we kind of simulate certain conditions to test them, right? So we can fabricate the scenarios to in such a way that they put these features to test. And this tool also helps us to verify the data. Once the participant has driven through the simulation, we make sure that the whole data has been captured, and this tool allows us to do that. And and coming to the data extraction, I'll be talking about it in a little bit once I discuss the minisim first. So after the ISAT generates a scenario tool, which we call is the final product, it is exported into minisim. So minisim is where we basically handle the simulations. So it lets us choose different simulations, that scenarios that we want to simulate on the driver simulator. So in this study, we basically use three, which we'll be discussing later. And then it also allows us to select different types of vehicles, like regular passenger cars, sports vehicles, or pickup trucks, or luxury vehicles also. And once a participant finishes driving, it generates a driver behavior profile, or which is basically a data acquisition file. So this data acquisition file can basically be imported into ISAT, which we discussed, the second tool, to extract data. So that is what I was going to discuss about the data extraction. So coming to the scenario fabrication, we had three different type of scenarios, and like I mentioned earlier, they are urban, rural, and freeway. So in the urban scenario, the urban scenario basically consisted of like 4-lane, 2 lanes on each side, undivided arterials with intersection elements, and regular vehicles that you see on urban roadways, like passenger cars, school buses, and motorcycles, pedestrians, and so on. And for coming to the rural scenario, it consisted mainly of rural roadways, like county roads, with some passenger vehicles, pickup trucks, and a few semi trucks as well. And coming to the freeway scenario, it consisted of 2 freeways with 2 different speed limits, and 4-lane freeways divided, 2 lanes on each side, and a ramp to transition from one freeway to another freeway. And coming to the weather conditions, we basically simulated 2 types: rainy weather conditions and clear weather. And coming to the lighting, daylight and nighttime as well. And coming to the features, advanced features that we simulated in this study included 2 types: warning features and automated features. Warning features are those which basically warn a driver of a potential hazard or prompt a driver to make a corrective action corrective action during driving, whereas automated features assist or pick up certain driving tasks and can perform the tasks with very less intervention from the driver himself. So coming to the warning features, we simulated 3 types. The first one is lane departure warning. The lane departure warning basically warns a driver of a particular when the vehicle is going out of the lane. So as you can see here in the simulation, you can see a flashing text when the vehicle was going out of the lane, and it prompts the driver to correct his position in the lane. And coming to the next one is the blind spot warning. This feature shows a small light near the rear view screen mirror, side mirror, when there's a vehicle in the blind spot of the driver, so that the driver can make proper judgment as to when to make the lane change or to yield to the vehicle. The next one is overspeed warning. This feature was set up to display text as well, flashing text when the driver is going beyond a certain speed limit that was set by us. So as you can see there, it's flashing when the driver goes beyond a set speed limit, and so that the driver can make a corrective action and slow down. Coming to the automated features, we had two types. The first one is adaptive cruise control. So what this feature does is it maintains a set speed until it encounters a vehicle in front of the driver. So based on the speed of the vehicle in front of the driver, it adjusts its speed to maintain a constant headway that we can feed into it. So as you can see that it initially slowed down to adjust the high headway and then maintain the speed. Coming to the next one, it's lane keep assist. So this feature basically nudges the vehicle slightly when it's going out of the lane to keep it inside the lane, and so it's slightly nudges the steering as well. So the vehicle comes into the lane and stays within its lane. So coming to the data collection, we collected data including a total of 51 participants. 62% of them were males and 38% were females. And coming to the age segregation, 46% of them were young drivers aged between 16 to 25, and 54% were aged over 25 years. And we assigned the different types of advanced features to the participants in random to avoid any bias in the study. And along with the ADAs, both the lighting and weather conditions were assigned at random as well. So that we made sure there was no bias at all. And then each participant drove all the three scenarios, and from there we collected the data and we analyzed. And Dr. Pulugurtha will take over from here.
Okay, here are some quick results summary. First, to discuss about the warning features, our observations indicate that driver behavior suddenly varied with the type of driving scenario, whether they were driving a rural scenario, urban scenario, or freeway scenario, and the type of warning features that were in the vehicle. We observed longer headways, but more lane departures at nighttime. So likewise, observations also indicate longer headway, but a less aggressive lane changing, braking, and turning maneuvers observed during, let's say, rainy weather condition. And when you're looking at longer headways or less aggressive, that kind of indicates like a conservative mindset of the drivers, which may be true in some cases, which may not be true in some cases. We also observed that drivers above 25 years and male drivers showed aggressive driving behaviors, and literature certainly kind of like prompts or says that male drivers are generally more aggressive than female drivers. And when we are talking about these aggressive driving behaviors, we're specifically referring to braking and speeding or overspeeding. In general, warning features certainly had an influence on braking. They certainly had an influence on lane changing and turning behaviors, in addition to serving their intended purpose. If we were to look at, let's say, the results of automated features, what we observed is that these automated features certainly improved braking, lane following, and vehicle handling in all the three scenarios, whether you're looking at urban, rural, or freeway scenarios. If you look at LKA, or lane keep assist, it certainly seemed to improve the braking performance and lane following behavior compared to lane departure warning system. So likewise, if you look at automated feature like adaptive cruise control, that certainly seemed to improve braking behavior compared to both blind spot warning and overspeed warning. However, what we observed is more aggressive car following behavior in, let's say, drivers when they are driving a vehicle with automated features. So look at like overall, we observed variation in driver behaviors, which seem to have reduced by over 50% compared to the warning features and no advanced driver assistance systems. So overall, what we can conclude is that automated features certainly work better than warning features, again, which are certainly better than no advanced driver assistance system. So it seems kind of like we're heading in the right direction, and projects like this, I think, would add valuable insights that could be used, let's say, to improve the functionality of these advanced features. That's pretty much what we have for our presentation, and we'll be glad to answer any questions.
Srinivas and Raghu, thank you so much for those really interesting findings. I certainly invite our guests to submit questions through the Q&A feature or the chat, but there were a couple of questions that were submitted earlier. So I thought I would start with those. So, you presented some very interesting findings, and I was wondering, did any of the findings surprise you in terms of being not what you expected, or out of line with kind of what you've seen from similar studies?
Quite honestly, I'm not, but I'll let Raghu handle it because he's the one who closely worked on the research project, the literature review. So rather than me sharing my experiences or thoughts, let me have Raghu answer this question.
Thank you. So, no, we kind of basically expected what the results would be. So let's say for example, drivers, younger drivers were seen to be less aggressive or compared to drivers aged about 25 years. But if you see, they are more familiar with the technology that they're growing up with, or they know how these systems work, and they respond better compared to elder drivers. So I wouldn't say we were surprised. So we were kind of expecting some, but though this research finding might not align with the previous ones, but I think that was kind of expected.
It's interesting. So the years that my kids have spent playing video games might actually be beneficial with more automated features and things like that. So another question, your study kind of looked at driver behavior and the impacts of these automated features and warning systems in different scenarios, including both urban and rural areas. Do you think that automated features need to be adapted for vehicles or drivers that will be used in some of these different areas, such as, city taxis versus long haul trucking, that kind of thing?
That's a good question. I mean, based on findings from our study, as well as ongoing developments, I think there should be restrictions or limitations as to where vehicles with automated features should be used, or let's say the automated feature should be on. I mean, no matter where, right now, at least at this point of time, we're still talking about the driver being able to take control of the vehicle, right? All the time. Mm-hmm. We are not at there where we can say, hey, if you are on freeway, you don't have to worry about taking control of the vehicle all the time. That we are not yet there. But what we found is, like, for example, on certain types of roads or in certain areas, for example, urban areas, in familiar conditions, it suddenly seemed to work better, right? And a lot of times, if you look at like real world, let's say crash data or other incidents that are kind of noted, you'll see that a lot of issues pop up because of, let's say, unfamiliar conditions or all of a sudden arising conditions. And I don't think the vehicles are there yet to kind of detect all those kind of scenarios. To me, it doesn't matter whether it's city taxi or long haul truck. To me, it's more the condition in which that particular vehicle is in. Of course, if you're looking at, for example, truck platooning, yes, that suddenly seems to be a viable option, but most of the times we're talking about those kind of like options on freeways, right? So which with relatively less conflicting situations and more, let's say, controlled setups. But again, in general, the diversity is what makes this issue more complex. We're talking about, let's say, vehicles with these automated features or advanced features. We're talking about vehicles without these advanced features. And the complexity arises because of, let's say, not just the different types of vehicles, but the different types of road system users. Can the technology pick up? I think we are heading in the direction, but we are not yet there right now.
Great, thanks. So there was a comment in the chat about how this research might be really of interest or aligned with that from some of the research that car insurance companies were doing. So I thought maybe we could broaden it out and say, this type of research, how is it being used by different industry entities, whether it is insurance companies, government regulators, manufacturers, those kind of things.
Right, and if we were to look at, let's say, the research, it's specifically, you can look at it from two different perspectives. One, perception, right? I mean, are people really willing to, let's say, accept the technology? Do they really understand the technology? Do they understand the functionality of these advanced features? That's primarily the focus. But if you're looking at it from, let's say, vehicle insurance and vehicle manufacturers' perspective, I mean, they could also kind of like maybe use the findings to identify where it works or where it doesn't work, or the gaps, right? I mean, it's kind of like a gap analysis, right? Okay, I mean, at least based on the perceptions, based on the findings from this research, when you're looking at like these specific scenarios, maybe drivers are not ready, or maybe we may have to look at it from a different perspective, or even if the vehicle is in automated mode, right? I mean, the question arises because the vehicle is in automated mode, who's at fault? You're expecting the driver to pick up. Is it the driver's fault, or is it the vehicle owner's fault? I mean, not the vehicle owner, but vehicle manufacturer's fault. Or should we kind of put it on the infrastructure? I don't know. I mean, so it will at least help minimize those gaps and address, or at least kind of like say, in these kind of situations, even though the automated feature is available, it's on, maybe drivers still will have challenges, right? So it will certainly, it can be used to address those kind of answers.
Great, thanks. So we have a question that was posted that talks about, in fact, we were talking about this, Srinivas, before the webinar started, but the different types of driving simulators that are available in the market. And, you know, when you're doing this kind of research, what are some of the challenges with researching and using the simulators? How does the system that you use compare with others? And then how realistic, just in general, are simulators to real world experiences driving?
That's again a good question. I'll take a crack at it and let's say Raghu, who kind of worked with the simulator, talk more. But certainly, let's say one of the greatest challenges when it comes to a project like this is mimicking the technology, right? And building scenarios that could be used to test the functionality of these advanced features in the vehicles. And that's not like, it's not an easy thing. And of course, if you have a much more advanced simulator that has the ability to mimic all the, let's say, types of vehicles that we encounter or we see in the real world, that would be a perfect setting. But I'm not aware of maybe a simulator that has all the different types of vehicles. And of course, it cost, right? I mean, let's say if you're looking at like low fidelity simulators are kind of less expensive, but if you're looking for high fidelity simulators that can kind of like do all the advanced research that you're looking at, I mean, they probably are going to, they're expensive. I know these simulators kind of cost anywhere from, let's say, $50,000 to as high as like $500,000 or even more, right? So it's but again, they come with, at least I heard that some of them come with, let's say, these advanced like features that you can rely on. You don't have to build upon it. But personally, I mean, I would like to build my own tools because that's the tools that I develop and I know how they function and what needs to be done rather than something that's off the shelf. I mean, there should be a balance between the two is what I'm saying. I mean, we don't want to simply take, okay, whatever is in the, let's say, simulator, kind of like provided by the simulator and just use it. We want to be able to kind of like, I don't know, modify the codes, work on advancements or kind of improve the functionality. But the other biggest challenge, obviously, I mean, we could have done more, we could have explored, I mean, if not for, let's say, certainly funding is one thing, but also the impact of COVID, right? I mean, that certainly had an impact on the number of participants because a lot of times it also depends on the number of people participants that you could bring in to collect data. And we got to do that, not just like just bringing in participants, but we also have to make sure that they're following COVID protocols, make sure that it's safe for the participants as well as the researchers in the lab. I mean, work from home, so not a whole lot of people were willing to kind of, let's say, participate in the study. So that's another challenge. But primarily simulator, again, there are some high-end simulators that have the functionality. Would they be able to mimic all the situations? I don't think so. I mean, but at least there should be some customization. Raghu, do you want to add anything?
Yeah.
Yes, I wanted to add a couple of points to Dr. Puluguta's answer. So the first one, based on we did a few some literature reviews. Some of the literature said that there are three factors that mainly matter when you're using a driver simulator to simulate it as close as possible to real world. The first one was high definition screens. The second one was the sound, that the ability of the driver simulator to generate the sound of the vehicle actually driving. And the third one was moving base, like vibrating when you're actually driving, to give you that feel. So these three, if based on these three, their experience improved. So actually our driver simulator actually has all these three. And in addition to that, when participants were driving, I had 2 or 3 participants who actually turned their head back to check if there was a vehicle instead of looking in the simulation as well. So when they're doing that, some were confused and they looked. So I guess that kind of answers to it.
Thank you.
The setup is very important. The simulation setup is very important.
We're hitting right at their edge, but there was one question and I wanted to bring it up. So maybe pose it and a real quick answer, and then we'll wrap up, because your age break was at 25. So, 16 to 20, 25 or so, 16, 24. But the question is, do you think elderly drivers will be more or less enthusiastic about these automated features in the future? And I don't know if your population of respondents was enough to allow you to test with that older group. What do you think?
It certainly does. And I think one of the challenges that we had, but we didn't have, I think we only had like 3 or 4 participants that were like 60 or above. So we didn't feel that it's a large enough sample to kind of like do a specific analysis. But yes, I think it certainly would have a different. I mean, if you were to look at elderly drivers, I would expect like results to be kind of slightly different than general adult drivers.
There was a couple more put in the chat, but I'm going to ask Raghu if you could quickly respond to James in the chat while I wrap us up. Because at this point in time, our time has come to an end. Srinivas and Raghu, thank you. I can tell based on the questions and the conversation, we could have gone on much longer. So I hope that everyone participating today will take an opportunity. The final report on this research will be published fairly soon, so that will be out and available. Keep an eye on our website and announcements that come through our MailChimp distribution. Huge thank you to today's sponsor, Econolite. And our next research snap is called Accessibility Policy for Autonomous Public Transit. It will be on December 9th at 10 a.m. And I look forward to seeing you all there.
And thank you, Hillary, MTI, Irma, for all the help, support, putting together the flyer, everything, and Econolite for co-sponsoring the event.
Great.
Thank you.
Thank you, everyone.
And to quickly answer those 2 questions, I know, Raghu, I was expecting you may be typing, but more aggressive, suddenly, we looked at adaptive cruise control, and car following was one of, let's say, the aspects that was looked at in addition to speeding when it comes to aggressive driving behavior. And did the simulator do continuous lane keeping based on the feature? Yes.
Great. Thank you. All right. Take care, everyone. See you next time.
Thank you all.